Hello everyone, I'm Jonathan. I thought I would present something that's related to my work. I work with a small data science consultancy. We do a bunch of work with insurers, and we do a lot of work with smallish data. So hierarchical methods and Bayesian methods are interesting to us. I put this talk together, like I do many talks, as a method of basically learning it myself. So I'm far from an expert. Been using PyMC3 for a couple of years, but PySTAN I'm quite fresh in. I thought it was quite interesting to perhaps compare, contrast, and talk about them. So there's three things I want to do. It's going to take possibly way more than 30 minutes, possibly not, but all of this is actually up on GitHub as well. I want to follow on from Tom's fantastic intro to probabilistic programming, where is he? And just share a few more thoughts on Bayesian inference. Show you a few of the capabilities and talk about PyMC3 and STAN, PySTAN, and possibly think about getting involved. So we've seen some great stuff already. Bayesian inference tells us more about the why and the how. How are these outliers different? Some stuff that I did as a random task for Ian the other day when he was talking about his sneeze statistics was to try a Bayesian Poisson regression to see if I could determine if alcohol affected sneezing. And that's the kind of stuff you might get into. There's the changes in conversion rates, and what we're talking about today, just a little bit, and apologies for the size of these, they're a bit small. Can we create a linear model and determine whether cars from a certain manufacturer are more or less emitting? And maybe we can discover if Volkswagen are misbehaving. I think Mitsubishi now as well, which actually comes up in the data. You'll see that a bit. Everyone draws this. This is my version. Traditional stats, white box modeling, looking at stuff that you could do in Excel or on paper towards one end. Black box modeling, where highly complex computation at the other end. And you don't really care so much about how the model what's actually going on inside. You just care about the test results. I see the Bayesian inferential work that we can do as sitting somewhere in between, because, like Tom said, you're able to introspect into the actual model construction and create your version of the world and the way that you think it works, and then press a magic button and allow some black box sampling or variational inference compute for you the probabilities that you're after. So two options that we have in Python framework are PyMC and STAN. STAN is supported newly by NumFocus. They're quite keen for me to say that. PyMC3 doesn't have a logo, but I just made one. Sorry, Tom. I don't use this. It's terrible. But I thought I should show something. Both of them let us do some MCMC sampling, and there's some convenience functions there. PySTAN and STAN are effectively one and the same. PySTAN is a thin wrapper around STAN. It doesn't do a whole lot itself. It does a couple of things that are very useful. But generally, when I say PySTAN, I mean STAN. When I say STAN, I mean PySTAN. Something like that. 5 minutes in, I'll jump straight to the conclusion. Which should I use? I want to do some Bayesian modeling. What should I use? What should I do? I suggest, apologies for the formatting on this, that PyMC3 is fantastic for rapid prototyping. Everything's in Python. There's no messing about compiling anything else. Everything's on your system. Everything works. And sorry, Tom, if this is saying entirely the wrong thing. But there's a bunch of really great features for plotting. Putting arbitrary functions in there, so creating your own likelihood functions. Tying in different external samplers. I foolishly tried to use the MC sampler, big ensemble sampler, with PyMC3 about coming up 2 years ago now. And it worked, which was great, but it was quite scary. And that's a big an ensemble sampler, very different kind of concept, which many samples are taken at a time, and they aggregate together to map out that posterior probability function, and arrive at the answer in a much quicker time. And it's not a Markov chain, so you don't have to worry about them getting lost. If samplers get lost in some well of probability, fine, don't care about them. You've got tens of thousands more. And that's some really cool stuff out from Dan Foreman-Mackey out of New York. It also has some nice things for information criterion calculations, leave one out cross-val, posterior predictive checks, post-modeling, so you can throw in new data. And you can do stuff like Tom just showed with using Theano shared variables to swap data around. So it's kind of fun. On the other hand, STAN PySTAN, and I say this as a relative newbie to this, to using STAN, has all the cool toys, the sampling and the inference and so on. And it does have huge academic support, and also, well, it's supported by NumFocus, so it has it has a nice logo. It seems a little bit more robust. I would feel more confident pointing at it with its static typed language and so on if someone was giving me a hard time about why a likelihood was a certain way around, or certain probabilities have been pulled from it. So probably start off with PyMC3. Certainly myself, I'm more familiar with it. It's a lot more simple to pick things out, and the code is a lot friendlier and more Pythonic. And possibly stand things when you wanted to make something a bit more production ready, possibly, and run models. And we'll see a bit later about the relative timing of these two. They're, long story short, they're similar enough on my machine. Both are open source projects. You can contribute to them. PyMC3 actually has quite a lot of stuff going on. 50 odd contributors, 4,000 commits. That's pretty great. One or two are from me, and most are from Tom, and the other guys. And STAN is a bit more mature. Also, something with STAN is this choice between PySTAN and PyMC3 doesn't really exist in the R world, where everyone seems to be more or less converging on STAN. So if you've got data scientists split down the middle between R and Python, well, this crowd in the Bayesian methods probably using STAN. So there is good momentum behind it there. There's a bunch of existing comparisons. Jake Vanderplas and Chris Burns from a couple of years ago. There's some stuff that I saw happened around the end of last year, released on Andrew Gelman's blog. And some chap who I don't know, Isaac Slavitt, did another direct comparison of PyMC3 and PySTAN. By the way, this is all up on GitHub, so you don't have to take notes. There's also this. Yes, there you go. This other. Number 3 was get involved. There's loads of growing momentum in this. STAN, PySTAN you can contribute to, PyMC3 as well. MCMC plotlib I'm calling out because I quite like plotting stuff, and I have it on the back burner task to start contributing to that a little bit more, which is some nicer graphing and plotting for probabilistic distributions and really interpreting the models in a graphical way. There's a project in R called ShinyStan, which does this, and it does it very well, actually. And it almost makes me want to pick up R again, but no. You could read more stuff from these guys. There's a longer reading list on a blog post that I made. You could join a meetup group. Big O London, Bayesian Networks London are two that definitely do this stuff. There's a new one in town called Bayesian Mixer, which I co-organise. And we've had 2 meetings so far. Third one is scheduled for mid-June. It's talking about stuff a bit like this, and worked examples in industry, academia, anything that's interesting, basically. Trying to just gather a bunch of nerds in a room, a bit like this. And yeah, next one's in June, so. Okay. We'll get on with it. Right, so what do I want to do? What do I want to do today? That was actually faster than I thought. That's good. I will look at some car emissions data. It looks a bit like this after cleaning. In fact, if I turn it around the other way, transpose this and add some information, you don't really have to know too much about this, but there's just over 2,500 cars in this car emissions data set. They have a bunch of, I'm in the way, aren't I? They have a bunch of features. The manufacturer, the brand, the model, basically a loose description of it, the fuel that it takes, some measurements of its fuel performance, some measurement, some categoricals on the transmission and whether it's a turbo diesel and the parent ownership company. There's also a couple of things on the emissions measurements. And what I've just plucked out of the air is I'm going to try to predict the emissions of nitrous oxide, NOx, not a nice gas. No one really wants it. If this is the thing that caught out Volkswagen, if you're definitely familiar with the story, but they and I think Mitsubishi as well basically faked their test results. So I wonder if we can perhaps determine that from something in the data. Maybe we can regress very simple linear regression on this value for NOx, and holding all other things constant, perhaps the fact that it's a manufacturer X or Y has some impact, some bearing. Just a handful of distributions on there. This is talking about what I was meaning. We have the emissions and we have a bunch of things that I'm going to use to try to predict this. Transmission, fuel type, engine size, other measurements of how efficient it is. The data set is reasonably balanced, but not massively so. I'm concentrating on VW again. So the actual manufacturer of VW is very few of those. Most cars are not from VW. But when you look at the parent company, actually quite a chunk are, because they own Audi and a bunch of others. And what else? Fuel type, I'm going to ignore hybrids. We're just doing petrol versus diesel. Transmission, flappy paddles or manual or auto. It's moderately well balanced. It's not perfect. The categoricals are kind of interesting. As for actual, you probably can't see half of this, but for actually what's there, most cars, the brand, the manufacturer is BMWs, Audis, Mercedes, Ford, Mini, and so on. Volkswagen's actually about number 6 just here. However, again, when we look at the parent size, BMW and Volkswagen are by far the largest. And actually, the cross plot of those, again, this is way too much, it's all online, is that we have, let's say, Volkswagen owning Audi, Bentley, Lamborghini, Porsche, Seat, and Skoda, and Volkswagen as well. So there's a whole load of brands underneath the umbrella. On the other hand, there's some things a bit like Mitsubishi, which only makes Mitsubishi branded cars. So you can see here, it might be interesting if we're looking at the manufacturer, these ones, to have some measure of the parent in there. So there is an inherent hierarchical structure in here. I don't want to say if your car is, an Audi, that's all I care about. I might as well care about the fact that it's made by a parent company. So, numeric features, they look broadly okay. This is a thing I'm going to try to predict. It's not pathological. There's a few outliers, and we're going to get rid of those. Engine capacity seems a little bit grouped. Perhaps worry about that. The point of me showing you this is to show that the data is not perfect. It's real, and it's a mess, and there's real problems. Some of these features that I could choose from, the metric combined, are highly correlated. So I'll perhaps try to choose just one or two of those. And in the repo, I think I go through a constrained lasso regression to try to drop out these features. I'll go through this just quickly. Looking at the categoricals versus the emissions, NOx. Again, they look reasonably well distributed. There are things like if you are a diesel car, you probably have higher emissions in NOx. That's just the way the engine works. That's fine. That's a detail. God, just out of respect for your eyes, I won't show this too much. But when you look at the actual cars and the car emissions, you get a picture of roughly where you expect the cars to behave as far as their emissions go. Audi, for instance, are very narrowly bunched, whereas, let's say, Mercedes-Benz have some cars which are branded Mercedes-Benz, which have quite a range of emissions. McLaren are there with just a single dot in the middle. You can look into all of this. The distribution of numeric feats, they correlate a little bit. There's going to be something in there. Just having a look at a t-SNE rep of this as well, just to get an impression of how distributed the predictor variables are in terms of the whole the whole data points, you can see that there are some hotspots in here. You're familiar enough with T-SNE representations, squishing down many dimensions into 2, and then being able to plot that. So points that are far away in high-dimensional space are still far away in this. It's kind of a clustering. And points that are close together in high-dimensional space are close together on this. So we see there are bunches of cars, each dot is a car, which have a high metric of extra-urban. There are, similarly, some which have a high engine capacity. And if you look at things like the manufacturer's VW, there are cars which are VW around about here in the input vector space. So they're a little bit clustered. Maybe this is modelable. It's not completely heterogeneous. Probably a linear model is wrong, but let's find out. So, okay. So, I'll load the data. I've cleaned it. I have divided it by 2 standard deviations, as Gelman suggests is a good idea. It puts your numeric features into the same variance as categoricals, or binaries. Describing the dataset, skip over that. Right, these are the features that I want to use in my model. That's what I'm trying to predict. That's what's going in. That's roughly the data type that I've got. So I've got some factors, Boolean, and some floats and ints in there. So it's a mixed bag. I've got 20 parent companies and 38 manufacturers. So this is how I can state, using a PATSI kind of syntax, my model. So my linear model, for a start at least, in the pooled model, is the emissions are something to do with the fuel type, transmission, whether it's turbo diesel, engine capacity, the combined performance, and the emissions of carbon dioxide. Carbon oxide. No, carbon monoxide. All right, so a pooled model. Pooled linear model. I state boldly that with that formula you just saw, that explains my my emissions. This is actually much less interesting than Dan Foreman-Mackay has very recently created this DAFT library, which lets you create plate notation. So I'll show a bit more of these as we go on, because what we're going to do is start making this more and more complicated as it gets more hierarchical. So what this is saying is, take all the features that we've got. There's a coefficient on each, standard linear regression. That's describing the mean of a normal distribution from which I pluck the emissions value. And this is saying exactly the same thing. I observe the emissions value. It's determined by this dot product of the coefficients and the data. The coefficients come from, they're shared, they come from some external single value across all cars for, let's say, the parameter on if it's turbo diesel. And there's a noise factor in here as well, a noise term. Okay. So PyMC3 looks a bit like this. I'm warming into this because later chunks of code that I show are messy because I've done some timing in there as well. This is the general gist. Now, I think this is yours, Tom, wrote a small module which takes the PATSI string, takes that model specification, and creates the priors and the likelihoods for you within the model, which is a nice lazy way, a very convenient way of specifying the model to let us say, this is, with my model, as an object in this context, make something from here. Here's my data set, and this is the likelihood function that I think it will be, and you go off and PyMC3 and do the rest. I'm using a student T distribution here, again, to try to cope with outliers. It's got fat tails. This is actually how the rest of my code looks, which is a bit of a mess, but you'll recognize this bit. And 2 bits where I'm trying to make a best guess of where to start. I'm far from an expert in why this takes forever, but it's an optimization technique to try to find the max a posteriori point at which to start the sampler off. It's not, sometimes that works, sometimes it gets stuck forever. So there's other better ways of doing it, including possibly the variational inference way. This bit is instructing it to take some samples. I'm going to take 4,000 samples because that seems like a reasonable amount. I'm going to use the NUT sampler. I'm requesting it in this case, in this only case, to run on one core and to not multiprocess. The reason for that is because I tried running it on 2 and it didn't work. PyMC3 is a little bit in beta still, and occasionally stuff goes wrong and you're not quite sure where it is, possibly in the multiprocessing or in speaking to Theano and scheduling jobs. So most of the time it works, but occasionally it doesn't. It's quite interesting to see when it doesn't. I don't mean that in a bad way. So, right. I can run the model. I can take my traces. These are the final 1,000 traces. These are the density distributions of those parameters. This is the marginalized posterior probability of the intercept, the values for petrol, manual, whether it's semi-auto, turbo diesel, engine capacity, and so on. So these are the, if I want to recreate my emissions, this is a linear model. You've seen this before. So if I want to, I could take the max value of all of these, multiply that by the values for each car, and I should arrive at roughly the emissions value. And the nice bit is, I think I've done this. No, you can see where I was making stuff up as I go along. Nice thing is, these are real distributions, as Tom mentioned. We have a credible region around each value, and we can compute various nice things, the posterior probability of the final results, and look even at each coefficient to try to gauge how tightly bound it is, and get a much better picture of what's actually going on. So the STAN model looks a bit different. Not in a bad way, but I'll come this side. What we're looking at here is the STAN proprietary custom, I guess, syntax, which compiles down to C++. It looks a bit like C or C++ anyhow. The model is this string, and what PySTAN will do for us nicely is take this string and go away and compile C++, which we can then run. It's a nice thin layer over the top of things. So we're able to declare the data going in there, the parameters. So, well, the data going in is, here you see the count of the observations, count of the exog features, the raw data going in, and the predicted feature that I'm trying to get out. The parameters within the model are this set of coefficients, this wide vector. The model error. Transform parameters is an option. I haven't used it here, haven't needed to. And then we just describe the model. So it looks quite similar again. Here's our noise. It's being pulled from a Cauchy distribution. It's actually being pulled from a half Cauchy distribution because I've declared a lower bound on it. So you see, that's the PyMC3 way of doing that would be to declare an actual half Cauchy distribution. This one is inferred. And then I'm pulling the results from a cross of my coefficients from a student t distribution with some error that we've seen. It's fairly straightforward. Generated quantities down here is for things like posterior predictive checks. And that goes back to something I mentioned before, which is that it's possible to do PPC using PyMC3 post-modeling, but with STAN it seems to be that you have to do it during the modeling. So we feed it a dictionary of some of the values, run it using something that looks a bit like this. It looks reasonably similar. I'm telling it, here's my code string. My data is in that dictionary that I put together. I'd like 1,000 iterations, burn the first 3/4 of them, and run 4 chains on 2 jobs. So it's quite flexible, quite possible to specify whether you want it multi-core, how many chains you want, usually more better, because then they don't necessarily get stuck in wells. and off you go. The results summaries that come out of it aren't especially pretty, but they're a good first step for diagnostics. So we get an impression of what the mean is for our parameters coming out and the distributions of them. You can also plot these. And that's more or less, as far as I've seen, where the niceties of PySTAN pretty much end. After that, you're on your own. You have to do your own plotting, more or less. So now, yes, well, I won't take too long going through these. We've seen the pooled model, which ignores the manufacturer. Clearly, that's no good if we want to call out which manufacturer is more emitting. The unpooled model, this is one version of that, where I put the manufacturer value onto the intercept. There's also a fully kind of unpooled version, where every manufacturer gets their own entire model, which is just basically the same as dividing up the data set completely into the 38 manufacturers and doing 38 separate regressions, which again is fairly pointless. So yes, this looks a bit like that. So with I should probably put these on a separate thing, but anyhow, what you see here is another plate. So this inner plate is per car, the outer plate is per manufacturer. So now I'm pulling this intercept from the manufacturer itself. In PyMC3, it doesn't look a whole lot different. I'm now declaring my full model. I'm no longer using Tom's GLM thing. I'm actually declaring each prior that's going in there and declaring my model, and, well, you've seen this bit anyway, it's fallen off the end. But the key bit is it's vectorized. This beta 0, this manufacturer that I'm using for the intercept, is now vectorized. This is a 38 long Theano object. And that's basically all you have to do to make this PyMC3 model unpooled, which is really nice. We can run it, we can see some traces. On the default plotting, this is more or less default plotting, everything appears on the same thing, so it's a bit messy, but it's a nice check to see what's going on. PySTAN, in contrast, I can still, for this one, use a vectorized form. I've got an encoding here on the manufacturer, and that's going into this extra beta 0, which I'm also declaring here. So the vectorization bit in PySTAN, or sorry, in STAN, is similar up to a point. And we can run that and we can view a fit. Great. The first thing that comes out, now that we have valuations on the manufacturers, is estimations of the effect of that manufacturer on the emission. And it's a robust regression, but it's still a linear regression. It's fairly dumb. Every manufacturer is free to float. Every value can free float. And what we see is things like, this is the count of, obviously, the cars as well. So what we see most of all is cars which are, brands which are present in many instances tend to have more narrowly defined credible regions. This is the mean value, by the way. Cars which are underrepresented tend to have quite wide estimates of the value. You know, there's only 2 Ferraris in the group, and the estimate of the coefficient value has quite a wide bound. Not especially helpful. Digress past the fully unpooled model. It turns into a mess. It gets very pretty plots, though. You know, if you like colours. So. A partially pooled model. I'll save you the rest of the stuff. This is the plate diagram again. Again, every manufacturer gets their own beta coefficient, their own intercept, but this time we're putting a hierarchy on that and saying that they come from 2 shared parameters which are higher up. So this is the partial pooling. This is saying if you have a value here, it depends on a little bit upon the distributions that are defining it outside, which are shared by all cars. So in this way, we end up with sharing power across the model. In PyMC3, that looks, again, still quite nice. We just declare that the mean and standard deviation of this prior have come from something else, and we declare that something else above it. And that's pretty much it. Quite compact. We run that, we find some stuff. Yep. I won't focus too much on the actual outputs of this. In PySTAN, it looks a little bit similar. Oh, bugger, it's fallen off the bottom, but you can just about see here, I've had to start doing some looping because the vectorization is not always quite clear. And this one was just about doable, but what I'm about to show you next caused me to bang my head on the desk for a number of days, trying to figure out how Stan decides that it wants to work. In the partial pooling, I've declared that PySTAN and PyMC3 perform pretty much the same. Great. And here we can see the effect of that shrinkage on the partial pooling. So now every car also pulls its distribution from some shared hyperparameter. And you can see the effect that it has on underrepresented cars like Mitsubishi, Ferrari, Lamborghini, and so on, which previously had wide and God knows where estimates that have now been pulled in a little bit more. It seems a little bit more robust. It seems more reasonable. So can we comment on Volkswagen? Well, yeah, a little bit. I'll go back just a tiny second. It seems Volkswagen is here. It seems to have a fairly tight distribution, and it seems to be higher than around average. So maybe, but there's other offenders. Mitsubishi, Subaru, McLaren seem to have far higher emissions. And again, there's no way of determining who's lying in this, but it's an interesting kind of way to get into it. Finally, a hierarchical model gets a little bit more complicated. Now I'm taking the parent into account. So again, I've grown this, I've grown this, I've grown this. Now I'm suggesting that this intercept on the manufacturer is not shared amongst all cars, but it actually depends upon the parent, and those are shared. And this finally lets us get to our understanding of the real world and that model. In PyMC3, again, it's actually quite nice, although I did have to phone a friend for some help with some of the indexing, but fundamentally you're still dealing with vectors, and it's still fairly straightforward. You run it, you find some distributions, great. With PySTAN, and this has fallen off the bottom, so I apologize, you'll have to look at the actual code yourselves. It turned into more of an indexing problem, and this really was a bit of a bang your head on the desk thing. So again, that goes back to me thinking that PyMC3 is great for testing stuff out. Stan is where you have the time to sit down and really consider stuff. What does this lead to in the end? Some trace plots. Oh, okay. A slight diversion onto model runtimes. They're approximately similar. The Stan model was way faster at computing the pooled model. This is for a similar number of counts, by the way, similar count of samples. Not sure why PyMC was a bit longer here. I think it was in the model compilation phase. But otherwise, they track similarly. It certainly wasn't hugely noticeable and a huge pain to use one or the other. I know that now this was timing the model build and the model running steps. And it seems that Stan, once the model is built, is actually extremely quick. So if you want to put something into production, possibly you want something that is pre-built, and choose Stan. Again, probably got 2 more minutes, I hope, and it won't take too much longer. This is the outputs from the hierarchical model on the manufacturers. And see, there's been a few changes around there. You know, things like the smart cars have been pulled upwards. They're part of Mercedes group. There's a few other changes in the order. It's hard to infer too much from that. But now we can also look at the parent group and see that as parents, we see that even McLaren are big emitters. Shanghai Auto came from nowhere. BMW, Mazda, and so on. Volkswagen are not that bad. They're kind of mid-pack. If we look at the XY of this, which is not necessarily true to do, but I thought this was interesting because you can see the families of cars now. So you can see McLaren out by itself. It's got a high coefficient value up on here. Mitsubishi, again, very high. Anything that's towards this end is a highly emitting car. The families that we've got are quite interesting. Okay, here's the Volkswagen group is in orange here, mid-pack. you see we've got within the family, within the parent group, we've got Volkswagen, Bentley, Audi towards the top, coming down in emissions towards Seat, Lamborghini, Volvo, Skoda and Porsche at the bottom there. So if you're buying a VW car, buy a Porsche, you're being nicer to the environment. And this is the kind of stuff that we're able to do because we have a hierarchical view of the real world, the real model. And that's that. So thanks, and everything's up here on GitHub if you want to go through it at your leisure. Okay, do you have time for a question?
Yeah, 10 minutes.
Okay. Go ahead.
Thanks a lot for sharing. Great presentation, I loved it. So, all models are wrong, of course. How do you know which one of those is the most useful one?
That's a very good question.
Which one's correct?
Yes. What I didn't show you, but what is in here, is it's possible to calculate various information criterions along the way and also do posterior predictive checks to find out how the model performs on held out data. So we can do the same tricks as we do in regular machine learning and do tests on holdouts and cross-validation and so on.
So which one performed better cross-validation?
On this one, I didn't actually do it yet. I did compute the wake, yes, and I come back to me. I'll actually commit that bit and put it up here. It's a good question. Apocryphally, I think it was the partial pool that performed the best of all.
Anyway, I think it's the best tutorial on hierarchical modeling I've seen. Thanks a lot.
Oh, thanks. Okay. Just, go ahead.
What would you point out as the main advantage of Bayesian inference in the setup of a hierarchical modeling?
What would I say?
What would you point out as the main advantage of Bayesian inference in a hierarchical model?
I've no idea how to do it in a frequentist modeling way. It seems horribly complicated to set up mixture models. Again, in the frequentist way, there's loads of assumptions that aren't necessarily true to your data. I've found that in the Bayesian framework, those assumptions are made obvious and clear, and it's a lot more of a natural way to do things. But
one thing is that especially in generalized models, in a hierarchical context, you have lots of convergence problems. You also have them in did you experience any big convergence problems in more complicated models?
Not really, no. In fact, I was able to use the NUT samplers for everything here, and that's usually a good bellwether, at least in my experience, because when NUT tends to fail, it's because something awful is wrong with some gradient somewhere in your vector space, and it seemed to perform well enough. Anyone? Go back. Yeah.
Does PyMC3 support kind of applying these chains on distributed numbers of computers, and how does that affect the burn-in or the methods of making burn-in?
Distributed computing for the MC sampling. It does? I'm reliably informed that yes, that's fine. Yes, no problem at all. Yes.
Any of the frameworks help you with determining or do you always have to use 5.0?
That's an interesting one. They, as far as I see, not massively. However, I skipped past a page plotting the autocorrelation along the sample lengths. Actually, no. So both do. So PyMC3 out of the box lets you plot autocorrelation, which is a nice lagged way of seeing how the samples correlate throughout their own history down their path, and that's a nice out of the box way to test if your autocorrelation is high. Well, either something's misspecified, or you need to burn more. It doesn't, as far as I know, have a measure of R hat, which I know STAN kicks out, which is another measure of autocorrelation, which you get basically for free in those printed summaries. And again, it's a kind of rule of thumb. If this R hat value is bigger than 1.1, then again you're overcorrelated. So there is stuff there actually straight away, but it's fine tuning, finessing. Anything else? Anyone else? No. Okay. All right. Thanks.